Hello. We're going to cover chapter 3.5, which is rational functions and their graphs. All right, so to go over what rational functions are, we've talked about these in some of the previous sections, but a rational function is any function, f of x, that looks like this, p of x over q of x, where p of x and q of x are polynomial functions. And q of x does not equal 0, because you can't ever divide by 0. Okay, so that's the definition of what a rational function is, and we've covered them previously. The first part of this chapter, we're going to be talking about domain, which is also something we've talked about before. So the domain of a rational function. And the first thing to note is that you can't ever have q of x equal to 0. If q of x equals 0, then you're dividing by 0, which is not allowed, which is bad. Okay, it's just undefined. You can't divide something to zero-sized parts. So when it comes to finding the domain of rational functions, we talked about this a while ago. The domain is all real values except for those which make the denominator equal to 0. So domain of a rational function is all reals except for those that make the denominator, which is q of x in this example, equal to 0. So typically, as an example here, they will give us some function, say x squared minus 3x plus 10 over x plus 1, and will ask us what's the domain. Well, the domain here is all real numbers except for whatever made the denominator equal to 0. X plus 1, when does it equal 0? When x equals negative 1. So x plus 1 equals 0 when x equals negative 1. So the domain of this function is all reals except for negative 1. So how we write that is your domain is from negative infinity up to negative 1, and then from negative 1 to positive infinity. Now you could use a union here, or you could just say all reals except for negative 1. There's different ways you can do this, but that's the domain. And we go about doing this. Now, sometimes the domain of rational functions is all real numbers, because sometimes the denominator never equals 0. Like if we had this rational function, okay, when does x squared plus 1, when does it equal 0? Well, there are no non-complex answers that make this equal to 0. There are no real numbers that make x squared plus 1 equal to 0, in which case, what's the domain? Well, the domain is all real numbers, because there is no real number that's outside the domain. So then the domain of this guy would be all reals, because there's no real number that makes x plus squared plus 1 equal to 0. There's no real number that can do that. Every real number, when you square, it's positive, so you're always going to get a number greater than 0, never equal to 0 in that example. So it's not to say that the domain of these rational functions are, that you expect them to be broken up like this. They can be, or they could be the entire real number system, number line. The other thing to note about this is that rational functions, you could almost think as polynomial functions as a subset of rational functions. You could think of this function here right? This is a rational function. Notice the q of x does not equal 0, it equals 1. Well, I mean, really, what is this? This is just x squared plus 4x plus 4, which means really we can think of simple polynomial functions as a subset of rational functions, just to let you know that. Okay. Okay. Now, before we continue, let's talk about kind of the most simple rational function, kind of the example problem they always start in these courses. And that is, we'll look at the function f of x equals 1 over x. We'll use this to kind of guide the rest of the process through this section. And we're going to do everything we can with this guy and then graph it and then talk about some of the things we can extrapolate from this function. It's called the reciprocal function, in general, to the general category of rational functions. And the first thing I'm going to notice about this is I'm going to create a table. And let's look at this table. So I'm going to plot it. It's going to be a normal t-table. I'm going to start, and I'm going to do it from a positive side and a negative side. So I'm going to start at negative 10, negative 5, negative 2, negative 1, and then maybe negative 0 point or negative 0.1. Where's that? Negative 0.1, and then make negative 0.1, negative 0.1. Well, what are the y values of f of x? Well, negative 10 is what? Negative 1 over 10. It's 1/10. What's negative 1/5? The next one's negative 1/5. Then we have negative 1/2. Then we have negative 1. Now, when you plug a 0.1 in there, what do you get? You get negative 10. And here you get a negative 100. And the last one's a negative 1,000. So notice that as you get close to 0, as we get closer and closer to 0, these numbers are getting larger and larger. And as we get closer and closer to negative infinity, the numbers get really, really close to 0. So if we were to graph this from the negative side, what you'd have here is, let me try to draw as straight a line as I can here. There we go. What we have here is that as you're going off to negative infinity, you're approaching 0 here, okay? And then you're coming, and let's say right here is 1, negative 1, and here's negative 1. So you're right there. And then we're spinning off to negative infinity. But we're never crossing x equals 0. We never actually get to 0 because as it goes off to negative infinity on the left-hand side, it approaches 0 but never becomes 0. And we never also cross y equals 0. So we're not crossing y equals 0 or x equals 0. Now let's do on the positive side. So now we're going to choose positive values of x. So we'll do 10, 5, 2, 1, 0.1, 0.01, 0.001. So 10 is going to give you 1/10. 5 is going to give you 1/5, 1/2, 1, then 10, 100, 1,000. So notice it's doing the same thing, it's just on the positive end. So again, it's approaching, as you get larger and larger, you're approaching 0. So it's starting here at 0, so you're approaching 0. And then at 1 and 1, that's where it crosses, and then it goes off as you approach 0 on the x value. So as you approach infinity on the x value, you're going off to 0, but on here you're going up to like that. All right, and that's the graph of this function. Now we can't ever equal 0 because 0 is outside our domain. So we can't, there's no value for, this is y equals 0, this is x equals 0. You can't ever get the line x equals 0. My bad. Okay, and this is called asymptotic behavior. So asymptotic behavior is where as you spin off to infinity or as you approach a number, either go to infinity or go to some constant. So we can talk about, and we'll talk about this, there's two different types of asymptotic behavior here. One is horizontal asymptotic behavior, which in this example is y equals 0. It's the x-axis. That's a horizontal asymptotic behavior. Notice as we approach that, we're spinning off to negative infinity and positive infinity as we approach y equals 0. And that's horizontal. And we also have, as we approach x equals 0, and this is known as vertical asymptotic behavior, we're spinning off to infinity. Okay? So to talk more about this asymptotic behavior, which is kind of the whole big thing with these rational functions, is this asymptotic behavior where it's spinning off and shooting off to infinity and not touching the line, or touching but approaching it at different cases. I'm going to talk about the simplest form. I'm going to talk about vertical first. So vertical asymptotic behavior is kind of the simplest form of asymptotic behavior. It's easiest to find. So we'll start there. So the vertical asymptotic behavior. Okay, what's a vertical asymptote? A vertical asymptote. Something has a vertical asymptote of, say, x equals a. So we have this x equal a is a vertical asymptote if, as x approaches a from the positive side. So what I'm saying here is as x approaches a, it doesn't touch a, but as it approaches it, then f of x will go to either positive or negative infinity. Okay? And vice versa, as x approaches a from the negative side, f of x will approach positive or negative infinity. So to have a the definition of vertical asymptote is that as you approach some value a on the x-axis, your function will spin off to positive or negative infinity. Our example above, as we approach 0 from the left-hand side, which is the a negative, so this is your left-hand side behavior, then the function spins off to negative infinity. And then as we approach 0 from the positive side, from the right-hand side, so this is your right-hand behavior, it spins off to positive infinity. So one side's negative, one side's positive. This doesn't mean they're always going to be opposite. Sometimes they will be opposite, like in this example. Sometimes they'll just both spin off to positive infinity, sometimes both negative. So don't just assume from this example that asymptotic behaviors are always going the opposite direction. They won't, and we'll do examples where they won't. Okay. So that is the simple definition of vertical asymptote. Well, how do you find them? So now we know what they are. Well, they're fairly easy to find. They're all the points that are outside the domain, where with one caveat. And so the caveat's what we're going to talk about. So to find a vertical asymptote, you need to find all the zeros of your denominator of q of x, where those are not zeros of p. So we're looking for all factors of q of x that are zeros. So we have the factors of 0 that aren't zero factors of the numerator. Okay, and if there is those, then they are vertical asymptotes. So let's run through an example. This might seem we're using big words here that we've never seen before, but it's really not that hard, and we'll go through some simple examples. I'll start with the very basic one. Okay, so here, this is basically the exact same one we just did, except it's we're kind of shifting it. So where does this have a vertical asymptote? Yes, it does. We look at the denominator. Where does x minus 1, where does it equal 0? Well, it equals 0 at x equals positive 1. Right? And positive 1 is not a 0 of the numerator. Well, the numerator has no zeros because it's a constant number. So this fits the definition. It's a vertical asymptote. So when we graph this guy, which is very close to what we just did, it now has a vertical asymptote at 1. This is 1. And other than that, it looks exactly the same as what we just did. It's just shifted, which should be what we'd expect. It's shifted to 1. So it's the same one we just did, it's shifted to 1. Okay, so that'd be kind of a simple example. Let's do another one. Okay. All right, so here's a little bit more complex. And where are the vertical asymptotes? Well, we need to set the denominator equal to 0, which we did. And we're going to factor it. Well, this guy's factorable. It's x plus 2 times x plus 5. And we're going to set each of these factors equal to 0. And when we solve them, we're going to get our zeros, which are negative 2 and negative 5. Now, do either one of these numbers, negative 2 or negative 5, are they also zeros of the numerator? The answer is no. Negative 2, when you plug it into the numerator, it's negative 8 plus 3, which is negative 5, which is not equal to 0. Same with negative 5. You get negative 20 plus 3, which is negative 17. So neither one of these will make the numerator equal 0. So indeed they are. They fit the definition of a vertical asymptote. And so we'll have two vertical asymptotes. One at negative 5 and one over here at negative 2. And we'll have some behavior, you know. I'm not going to graph this yet because we have more tools we need to learn. But this would be vertical behavior, so maybe it'll look something like this. Maybe, or something similar. Again, I'm not going to actually solve it. I could, but I'm not going to. Okay. So let's move on. Let's do another example of finding vertical asymptotes. Okay. So on this guy, we're finding all the values where the denominator equals 0. Well, there are two of them. There's x equals 2 and x equals negative 2. Now notice one of these does make the numerator equal to 0, and that's negative 2. When you plug negative 2 into the top, you get 0. So this guy right here, this fails the test for asymptotic behavior. So it is not an asymptote, but that's not to say it's not something special. It is something special. It's outside the domain. So basically what happens when you have something that's outside the domain that's not asymptotic behavior is you have what's called a hole in the graph. This guy right here is a hole in the graph. And what it looks like is you might be coming along, here you are, coming along, and you're traveling like this, and you get to what you'd think is an asymptote, but it fails this test. Instead, you get a hole. And it looks like that. So it's this hole in this graph where the graph just comes along. It's not spinning off to infinity, but it also doesn't exist. So it's just a hole in this graph. So that's what holes look like. So they are special type of behavior. You can have these holes in the graphs. And they are where the 0 of the denominator is also 0 of the numerator. So holes occur. Holes occur when x equals a. So this is a hole. A is a hole. when x equals a is a 0 of both the numerator and the denominator. So that's when you get a hole. If you don't have a hole, however, you have this asymptotic behavior where it's spinning off to infinity. Okay. All right. So that's talking about the vertical asymptote and how to find them. Okay. Now let's move to the next. If we look back at our original example, right up here, this guy here, notice that it had vertical asymptotic behavior, but also had horizontal. So let's talk about horizontal asymptotes. So what is horizontal asymptotes? Well, horizontal asymptotes are like vertical, and except that vertical, when you approach a number, when x approaches a, f of x goes to infinity. It's the opposite here. It's when x goes to infinity, f of x approaches a constant. So that's a horizontal asymptote. So difference is, if we look at the definition of vertical, where is it? It's right here. As x, you notice here, as x approaches a constant, f of x goes to infinity. So here in horizontal, it's as x goes to infinity, either plus or minus, then your f of x approaches some constant, some a, which is constant. Okay, so an example with simple case up here is as x goes to infinity in the ends, over here and over here, your x's are going to positive infinity here and negative infinity over there, so positive infinity here, negative infinity here, that your f of x is approaching 0, which is a constant. So it's not going to infinity. So that's when we have horizontal asymptotic behavior. Well, how do we find them? Well, finding them is a little bit more tricky. And before we do that, there's a couple things I want to mention about horizontal asymptotic behavior. The first thing is horizontal asymptotic behavior is not as rigid, which makes it a little bit harder to understand than vertical. Vertical asymptotic behavior, you can't ever cross a vertical asymptote. You can't ever touch or cross it. It's basically like this force field that's impossible to cross. That's not true with horizontal. You can have a horizontal asymptote. Maybe here's your horizontal asymptote. And you can be approaching it here, and you could cross it many times in the finite and then approach it like this. So horizontal asymptote's just wondering what it does as x goes to infinity, to negative or positive infinity. Is f of x then approaching a constant? It doesn't mean that you can't cross a horizontal asymptote. You can. Also doesn't mean that you might have one end where your horizontal asymptote might have one behavior on one end and another behavior the other, meaning it might not. You could have this guy here. There's such a thing where you might not have any behavior on the left-hand side. Like there's no behavior over here, but we're approaching 0 in the horizontal asymptote over here. It could just be because the function's only defined for positive numbers. So that's one thing. The other thing is that the other thing with horizontal asymptotes is if you have one, you're only going to have one. You're not going to have more than one. Verticals, you could have as many vertical asymptotes as you want. With horizontal asymptotes, if you have one, you don't always do, but if you do, you only have one. Okay? So that's the other difference. So the main difference are you can cross a horizontal asymptote. You can't with the vertical. So these are differences. The other difference is you can only have one or 0. either have 0 or 1 horizontal asymptotes. Where you can have as many as you want vertical. Excuse me. Okay. So now we know a little bit about horizontal asymptotes. How do we find them? Excuse me. Well, you find them, there's kind of this procedure. And what you do is you look at a function. Say you have some function that looks like and I'm writing this out in its more detailed form. All right. Okay, so you have this function, and it's a rational function. And I've written out like this. We have our numerator and denominator. And what you're going to do is you're going to compare the highest power. What is the power of the polynomial? You're going to compare n and m. Okay, and so you're going to have three cases. Case 1, n is less than m. If n is less than m, then you have a horizontal asymptote at y equals 0, which is the x-axis. So if n is less than m, so if the power on the top is less than the power on the bottom on the variables, then you do have a horizontal asymptote, and it's at the x-axis. This is the x-axis. Okay. Now what happens if they're equal? Then you have a horizontal asymptote, and the horizontal asymptote is at y equals the difference of the leading coefficients. So an over bm. So you take the leading coefficients and you divide them. Okay. And then the third case is what happens when n, meaning the power on the top is greater than the power on the bottom, then you have no horizontal asymptote. Okay, so example, best be to look at this example, some examples here. I'm going to look at this function here. Taking these three functions, and I'm just varying the power of the top. Okay, so first guy, does this have a horizontal asymptote? 4x over 2x squared plus 1. The answer is the denominator is greater than the numerator, the power. So notice this is a 2 and this is an understood 1, all right? So then here we have n is less than m, because 1 is less than 2. If we look at our rules, n is less than m, we have a horizontal asymptote of the x-axis. So we have a horizontal asymptote at y equals 0, which is the x-axis. Okay, now we move to the next one. Next example, notice the powers are the same. Okay, well, that's case 2, n equals m, in which case we have a horizontal asymptote at the difference of the leading coefficients, which is 4 over 2. So we have a horizontal asymptote at y equals 2. Okay, so I just took these and divided them, the leading coefficients. And the last case, n is greater than m, and we have no horizontal asymptote. Okay, so that's simply how it's done. Okay. Now, we're going to talk about one other type of asymptote. So the last type of asymptote, we talked about vertical asymptote, horizontal, and the last one is we're going to call slant asymptote. What is a slant asymptote? Well, it's where the asymptote is at a slant. It's like a line. So you might have something that you say have a vertical right here, and you might have a slant right there, and then your lines might be looking something like that. Okay. Try to do this a little bit better. Okay. So we have a slant. The slant asymptote is right here. So how do we find them? Well, you have a slant asymptote only when the denominator power, the power of the denominator, is exactly 1 greater. So if we look at the examples above, right here, this guy here, these two, this one here and this one here will not. They do not have no slant asymptote. This one, however, will. This will. So note right off the bat that if you have a slant asymptote, you will not have a horizontal, because in order to have that slant, the denominator has to be exactly 1 greater than, or the numerator has to be exactly 1 greater than the denominator. And this guy here is exactly 1 greater than that. So this will have a slant asymptote, but it won't have a horizontal. So you can't ever have both a slant and a horizontal. So that's one thing to note. Well, how do you find them? Well, let's do an example here. Okay. Okay, so first off, with this guy here, let's practice going through our techniques. Let's talk about the different asymptotes. So the first thing when you're talking about asymptotic behavior is find if it has a vertical asymptote. Does this have a vert? And if it does, what is it? What's the vertical asymptote? Well, it's when x minus 1 equals 0. When does that happen? That happens at x equals 1. So it does have a vertical asymptote at x equals 1. So there we go. Let's circle that. So there's our vertical asymptote. Now, does it have a horizontal? Horizontal. Yes or no? No, it doesn't. No horizontal. Why not? Because the denominator has lesser power than the numerator. All right, okay, so it doesn't have a horizontal, which means doesn't have to have a slant, but it could have a slant. So does it have a slant asymptote? And the answer is yes, because the numerator is exactly 1 greater in power than the denominator. Okay, so if you notice up here, this is exactly 1 greater than the understood 1 that's there. Okay, now if it had been x cubed plus 1, then we wouldn't have a slant either. We'd neither have a horizontal or slant. All we'd have is this vertical. All right, so now how do we go about graphing this guy? So that's ultimately what we want to do. Well, what I usually do when I'm graphing is I go ahead and graph the asymptotes first. Now this isn't the way I'm going to teach you later because I'm following the book, but when I'm doing it, I always do the asymptotes first. So I'll draw my coordinate system. I know it has a vertical asymptote at 1, so I go ahead and put that in. Here's 1, and here's my vertical asymptote. Okay. Does it have a horizontal? No. Does it have a slant? It does. Now, how do we figure out what the slant is? Well, to figure out what the slant is, you need to divide the function. You need to take x squared plus 1 and divide it by x minus 1. So to figure out what the slant is, you can take x squared plus 1 and divide it by x minus 1. So you're taking the numerator and dividing it by the denominator. Okay, so let's do our long division. Change our signs. 2x. Bring down the 0 here, plus 0. And notice that, oh wait, my bad, I'm doing this wrong. See, move too fast. There should be a 0x here plus 1. So then you have x plus 1. Now, x plus 1, how many times can we divide it by plus 1? Change our signs. We get 2, so we have a remainder of 2 over x minus 1. So here we did our long division. Well, this is our slant. So we have a slant of x plus 1. So I graph that. So x plus 1 crosses at 1 on the y and goes up by units of 1. So here it'll be up by 2. And it looks something like that. Okay. So now I have my slant and horizontal. Now to figure out where they are, I have to plot points. So now what I do is I draw a table. And I want points in between each section. Okay. So I'm going to take my values and say x. I want points around -1 around the vertical. So I'm going to do, or positive 1. I'm going to do, say, 5, 3, 2, 1.5, 1.01. And then we know at 1 there isn't going to exist. So then I'll go at 0.99, maybe 0.95, and then maybe 0, -1, -2, etc. And I'm going to plug these in and use a calculator. So you plug 5 into the, let's write what the function actually is. Function is x squared plus 1 over x minus 1. So if I start plugging them in here, so this guy, you're going to get 25 plus 1 over 4, which is going to be 26 over 4. Which reduces to 6 1/2, so that's 6 1/2. Okay, we can plug 3 in. You're going to get 10 over 2, which is 5. So at 3, you're going to have 5. 2, 4, 5 over 1. So you get 5 again. Wait a minute. So you plug 3 in, you'll get 9 plus 1, which is 10 over 2, which is 5. And you plug 2 in, you get 4 plus 1, which is 5 over, you get 5 again. Okay. And then at 2, or at 1.5, calculators, you will, how to do 1.5. 1.5 squared, it's going to give you, do our long division, since I don't have my calculator on me, not long division, long multiplication. So 5, 2.25, you get 2.25, 2.25 over 2.25 plus 1, so 3.25 over 0.5, which is, you're going to be going back up. So this is doubling this, so it's 6.5. So we're going back up. And then 1.01 is going to be even greater. It's going to spin off. So we know then we can graph these in this area. We know what happens here is it's going like this. Okay, and it's probably leveling off in that area there. Probably a little bit of a hump, and it's coming back up. Okay, so that's what we're doing in that area. Okay, now in the other area, when you plug in the negatives, so let's see negative 2. Negative 2 is going to give you 4, 5. So this will be negative 5/3. All right? And then 0 is going to give you negative 1. So it's right there. So what, and then when you get closer and closer to 1, you're going to spin off to negative infinity again. So it's going to look something like that. And that'll be our rough sketch. So that's how you go about doing that. But you have to figure out where it is. You know it's bounded by these asymptotes. But to figure out how it's bounded, how do we not know it doesn't look something like this here? Or maybe like in the green here, maybe it's like this here. The only way to test it is you need to plot some points. So you can't just use the asymptotes, you have to plot some points. And sometimes you'll get things that you kind of unexpect. Like I wasn't expecting to pick the 5, but I realized now that I see that it probably has a dip, and so it goes below 5, and I'm picking numbers on either side here. Okay, so I guess it's not unexpected. So that's your slant. So basic steps. Let's talk about basic steps for solving these. So the step process they having you go through in the textbook is one, they're having you see if it's symmetric. And symmetry is something we've talked about several times, so I didn't cover it in this lecture. So see if it's symmetric. Well, to see if it's symmetric along the y-axis, then f of negative x equals f of x. So that'll be symmetrical around the y-axis. So you might get something like this. This is an example of symmetric with respect to the y-axis, okay, of a rational function. What about symmetric to the origin? Well, we already had one that's symmetric to the origin. If you look back at f of x equals 1 over x, this was symmetric with the origin. And so with symmetric to the origin, it looks like this. And that's found when f of negative x equals negative f of x. And if we plug negative x into this function, you're going to get, what's f of negative x of this function? It's, well, negative 1 over x, which is equal to negative f of x. So that's what's symmetric with the origin. Well, this can be handy. I don't know why they have you do this first. There's so many that aren't symmetric with the origin or with the y-axis. But if it is, I guess it helps you simplify it. The next thing they have you do is find all the intercepts. Well, how do you find the intercepts? Well, you find the y-intercepts by setting x equal to 0 and solving. You find the x-intercepts by setting f of x equal to 0 and solving. Okay. Well, this is only interested in if you're interested in the intercepts. It just gives you some extra points, and you need points. One of the problems with this is sometimes your intercepts are undefined. Your intercepts are often a vertical or horizontal asymptote, like not always, but they often are in simple examples like the one above here. Had no x or y intercepts, because those were both our vertical and horizontal asymptotes. So finding intercepts can be difficult. And then the next step, step 3, is finding the asymptotes, which is really where I start. So we're looking for the asymptotes. Find all the asymptots, which is really what this section's about. So, and I first find the vertical, then horizontal, and then slant. If it has a horizontal, you don't need to check for a slant. If it has a slant, you don't need to check for horizontal. These two are mutually exclusive. All right. Okay. Then once you have your asymptotes, then you just have to plot a bunch of points. You gotta just do a T-chart and make sure you have points on all sides of the vertical asymptotes, in between all vertical asymptotes. And then step 5 is plot. Now, so let's go about doing this. Now that we know the steps, let's look at some examples. Okay. So let's start with this one. First off, is it symmetric? So following their examples, we want to know if it's symmetric. So is f of negative x, what does that equal? Well, plug negative x into there, you get 3 negative x squared over negative x squared minus 4, which is equals 3x squared over x squared minus 4. So we get the exact same function back out, which tells us that this is symmetric with respect to the y-axis. So it is symmetric with respect to the x. No, not to the x, to the y. Why did I say x? To the y-axis, okay? All right, step 2, find the intercepts. Well, okay, to find the intercepts, to find the y-intercept, you set x equal to 0. So plug x equal to 0 into there, and all you'll get is 0. All right, you get 3 times 0 squared over 0 squared minus 4, which is 0 over negative 4, which just is 0. So right off the bat, we have our y-intercept and our x-intercept. Now, could you have more? Yes, we could have more x-intercepts. So x-intercept is when y equals 0. Well, here, you just check the top. When does the top equal 0? When does the numerator equal 0? When does 3x squared equal 0? It only equals 0 at 0. So we got them all. We have one intercept, and it's going through the origin. Or the x and y intercepts in the origin, okay? So that's that step. We found all the intercepts. Now we have to find all the asymptotes. So let's look at this function. I'll write it again down here. So let's find the vertical first. Vertical is when x squared minus 4 equals 0. That happens when x equals 2 and negative 2. Okay. So we have our vertical. They're right here. Okay, we have our intercepts. Our intercept are the point intercepts at the origin here. So this is all the pertinent information we have so far. And we have that it's symmetric with the y-axis. Okay. All right, now let's look at at the function again. Notice that the powers on the numerator and denominator are the same. So using the rules for horizontal asymptotes, since they're the same, it's going to have a horizontal asymptote, and it's going to have it at the ratio of the leading coefficients. So it is going to have a horizontal. Horizontal is going to occur at y equals 3 over 1, because the leading coefficients are 3, and there's an understood 1 here, 1. Okay, so here's the leading coefficients. So it's 3 over 1. So we have horizontal at y equals 3. Now, since we have a horizontal asymptote, we don't need to check for a slant. Okay, now we graph it. So we put all this information on a graph. What we have so far is we have vertical asymptotes at -2 and 2. So we have vertical asymptotes here. And we have a horizontal asymptote at y equals 3, which is here. Like that. And the only other thing we have is we know it's symmetric, and we know it has a point at the origin. So that's it. So we know it's symmetric, and we have these asymptotes. Now, we need to figure out what it does. Well, to figure out what it does, we need to plot points. Okay, and we need to plot them in all the things. We know. So what we're going to do is we're going to plot it at 5, 3, and then 2.5, maybe 2.1. That'll give us in this region here. Then we're going to want to do in this region here. So we're going to do at 1.9, 1.5, maybe 1, 0, which we already know is 0. And then, okay, and then we're going to stop. Now, why am I going to stop there? Well, I'm going to stop there because I know it's symmetric with respect to the y-axis. So whatever it does in this region here, it's going to do the same thing over here because of its symmetry. So that's the advantage that symmetry has, is it gives us what it does on the downside, and we don't have to plot a bunch more points. So plugging the points in. So what does 5 do? Well, 5 is 3 times 5 squared over 5 squared minus 4, which is 75 over 21, which is approximately equal to 3. Okay, it's a little greater, so it's 3.1 maybe. Okay, so that tells us it's above. So at 5, out here at 5, it's approximately right there. What about at 3? Well, 3 is 3 times 3 squared over 3 squared minus 4. So 27 over 5. Well, that's a little bit greater than 5. All right. So that tells us it's going up. So here at 3, it's right up here at 5. So we know it's going something like this, up this direction like that. Okay, I can plot the other points, but I already know it's going to go off to infinity. Okay, and since we know it's doing that over here, we know it's also going to do the same thing over here, like this. It's going to go off to infinity that direction. Okay, now what about in this region, 1.9? 1.9, so 3 times 1.9 squared over 1.9, 4. This is going to be less than 0. Wait. So this is going to be some number less than 0. So 3.61. Yeah. So 3, 18, 10.83. So it's 10.83 divided by 3.61 minus 4. So it's definitely less, and it's going to be large. Okay, it's going to be down here somewhere. So we know it's coming from down here. And we know at 1, it's going to be at 3 over negative 3. It's going to be at negative 1. So right here. So we know it's coming like this, and it's going to touch here. And then since it's symmetric, we know it'll come around and do the same thing over there. And that's what our graph will look like. It'll look, if we want to clean it up, look like this. Okay, so that's how this is done. If you have questions, feel free to call or to email me. I guess you don't have my phone number. Email me or talk to me on Zoom on at 10 in the morning or at 4 at night. If you need other times, just email me and let me know. Thanks. Hope you guys